Okay, that's been welcome at the first session in week 2. I hope week 1 went nice and smooth. I hope you got familiar with the course and you did complete the first assignments. If you have any question, always you can of course use the discussion board or you can email me. But I saw that most of the students had no problems, which is good sign. You did probably notice I changed the first homework assignment on WebAssign. I changed the due date. It's due this Saturday because we did have a few technical issues, and I didn't. That means I assume that you just need more time to navigate well with the WebAssign. Okay, that's one thing. And I also check the activity report, which I can see how many times and how often you log in. That means I can tell you, in order to be successful in online class, you have to be a little bit more engaged, a little bit more active on our Canvas page. Okay? Try to log in every day. Try to check the required documents. I mean materials and documents files provided. I did create, at the bottom of all of the modules, I did create additional modules, which I called Practice with Kasia. And I will just solve a few problems. I will make a short video, and I will always post this. That means it's really, really helpful to check these problems. Okay? I'm just doing for you to have extra things to practice. That means always make sure that you understand the problems that I'm solving for you. Okay? They are really helpful for your weekly assignments and of course for the midterms and later for the final. Okay, no more announcement. I can use the announcement thread, or I can use the discussion, or I can email everyone. Let's start the session. That means this week we are planning to cover section 1.8, which is continuity, and it's the last section in chapter 1, and we will start chapter 2. In chapter 2, we will cover section 2.1 and 2.2. And I think Sang-Hoon, the other instructor, will cover section 2.1 today at 6:30, and tomorrow at 6:30 he will finish 2.2. Okay? And please remember, if you can't attend the session, always make sure that you're watching the session. The link is provided. I am recording even now. It's not an edited video, it's just the live stream. Whatever happens in our classroom, it is recorded. That means make sure that you're watching. The most important source of the information are here, are happening in the classroom. Yeah? Otherwise, it will be pointless to have an instructor. We're really trying to give you a good instructions. Okay, we do have a question. Yes, the guided study session is also recorded, but I don't think we did have the session. Did we have the session this Sunday? Because I didn't see a link. I can double check because we should have it. Because I know that they always start, because I keep getting emails also from the University Park guided study leaders, and I think they starting the second week of the class. That means for the first week, I'm just assuming, I think Olivia, I don't think she ran the first session. Or if she did, I will make sure that you have the link provided. Okay? Daniel asked this question. Okay, that means we can start. One more thing, I did change the time because I think 9 o'clock was, 11 or maybe even midday, 12 o'clock. I will accommodate more students, but you remember what I said, it's not even possible to accommodate everyone because it's the online class. That means everybody has the flexibility to attend maybe the session, maybe not attend, but watch later. Okay, that means I will probably for the next 2-3 weeks, I will still try to maybe change the time, 1 hour plus or minus, because I still like the day session. You have one evening and one day session. Okay, but again, please watch the session and look at the info. Stay up, look for the information that are given. Okay, because they are really helpful and they will really give you success. Okay, no more question, we can start. That's mean what we have. We do have continuity, and let's see, I will just minimize everything. Okay, that means we will talk about the continuous functions and continuous like things that we may think that they are continuous. That means first of all, I can change my slide. If we will think actually about a function, we can think that I'm drawing something, and I can even draw something for you that like without any like interruption, without any change. If I would like to draw continuous function, continuous curve, I will draw something, let's say like that, and this requires me like to keep the pen on the paper. As soon as I like remove the pen from the paper and I come back, I mean, I can always come back to the same place and draw something, but this means that I did some like interruption. Continuous curve is the curve that I can draw without lifting the pen, like by one go. That's the easiest, yes, the easiest way to remember. Something continuous, no gaps, no jumps, no removed points. Okay, that's mean now from the mathematical point of view, let's try to define continuous function. Okay, that we can see, I do have a blue curve, okay, and that curve doesn't have any breaks, any asymptotes, any removed points. It's nice and smooth curve, continuous curve. But from the mathematical point of view, what is important? Let's look at one point. That's when we did practice limits and the values of the function. That means we have to make sure that for every single point on the curve, okay, the limit of the function at that point and the value is the same. That means I can say as x goes to a, that means the limit of the function at a, the behavior of the function as x approaches a, is exactly the same like the value. Because we remember limit is just like we approaching, function is approaching that level, that height. Okay? But value is the exact point. And we can see in this case, it's actually true. Yeah. Limit is the same at the same level that the solid dot, the value. That means pretty much this is the definition. Okay? That's the definition of the continuous function. And we do have most of the physical phenomena are usually continuous function. We don't really have like discontinuity. We may have discontinuity, like for example, probably everybody will give me this example, electric currents, right? Because we may have a stop at some point and then it will continue again. Okay, that means this box is pretty much what we have to check. I mean, let's see, that's the full definition. But you can see this is mainly, or even, I mean, I typed the same. That means, first of all, checking if the function is continuous at the number a. Number a must be in the domain, because if it's not in the domain, of course, we're not even looking at this point. If it's in the domain, normally the value exists. That means f of a is defined, exists. Then we're calculating a limit, and limit must be also a finite number. Limit must exist. And then we're checking the value and the value of the limit, the value of the function at a and the value of the limit at a. If these numbers are the same, we can say function is continuous function. But one more comment, we know what the meaning of the limit is, right? We know what is behind this. Limit is never the same like the value. It means that function is approaching that value, that height of the function. Okay, that means please remember we are saying that is the same, but it's just the shortcut. Okay, but we know the meaning, we know the definition of the limit. That means let's see. One more thing, what we may also have, we may have something which is probably a little bit weird for you at first, but based on the definition, it will be correct. That means we can define continuity from one side, from the right or from the left. I mean, let's say I will give you a function. At A, the behavior is like that, 1, 2. And let's say this is solid. Okay? And this is my function, f of x. That means, what do you think? Looking at this function that I just drew, do you think this function is continuous function? Do we have continuity? Oh, you can answer using the chat box. That will be nice. Yes, I can see who is attending the session. We have quite good group. Excellent. Okay, Samuel Bradley. Okay, Ryan is actually saying the right thing, but overall, yeah, the answer is no. It's not continuous. I did lift my pen and I draw like the other part. That means we do have this continuity. But you can see what is my point. I can ask you these two questions. What is the limit as x approaches A from the right-hand side? Can you tell me the limit of the function? It's 1, 2, or maybe does not exist. It's 2. We can see on the right-hand side, we will walk up to that point, and it's 2. And what about the value of the function at A? Can you tell me the value? It's also 2. Thank you. Oh, 1. No, we can see the solid dot. Always the solid dot represents the value. That we can see. That's it. That's the definition. That's how mathematics, like how we operate. We always defining things, and then we using this definition as a tool. That means value of the function at A is 2. Value of the limit at A from the right-hand side is 2. That means I can say, and they are the same. We kind of know what this 2, I can use maybe blue color. Right? That means the Bluetooth represents the limit. That means we just approaching that big solid dot, but this is still 2. That's what I was saying. I hope, and I'm sure you understand the meaning of the limits. That means this means that function is just approaching the level 2, but it's 2. And the value of the function is the exact dot. It is 2. That means if they are the same, I just wrote 2 and 2, then we can say that function is continuous from the right-hand side, at 2, of course. Okay? That means this will be like a one-sided continuity. And I can do the same thing on the left-hand side. But I hope you understand. Let me put something like that. I will pick different values, just not to be confused. Yx, and this is f of x. Okay, that means we can see I want this to be 5, and this is my a. That means limit of the function at a from the left and value of the function. That means looking at the second graph, can you tell me the limit at a from the left-hand side? What's the limit on the left-hand side? It's 1. Okay, we're looking at the second graph. Okay, it's 5. We can see function from the left-hand side is approaching that level, 5. Excellent. And what is the exact value? It's also 5. That's we can see the blue 5 theoretically is different than the red 5 because they have different meaning, but they are the same. They're exactly the same, like the same. I don't want to say the same point. Okay, that means I can say that we have continuity from the left-hand side. Okay, I think you understand this. That's mean now what we will do. We will take this function, nice function, okay, I draw it for you, and we will try to find out all of the points that function has discontinuity. And we will try to justify why function has discontinuity and possibly find out what type of discontinuity. Okay, That means, first of all, can you tell me the numbers that are not in the domain of the function? Can you tell me the numbers that are not in the domain? Let's assume that function is going to the infinity. Okay, and this is my f of x. And what numbers are not in the domain? Okay, definitely 1. 1 is not in the domain. Definitely, oh, is x equals to 3 not in the domain? I know that number 1, 3, and 5 are really important numbers for the question, but for the moment, yes, at the moment, I just want to find out numbers that are not in the domain. And we can see, if I draw vertical line, I will intersect at 3, I will intersect the point -1. That means we do have a value at 3. If the value exists, this means that the point is in the domain. The same thing will happen at 5. If I will draw a vertical line, the value at 5 is actually 5. Okay, but I believe I did put 7. I believe 7 is not in the domain. Yes, we can see we do have an asymptote, but 3 and 5 are important points for this question too. Okay, that means 1 and 7 are not in the domain. That means we definitely have to investigate what is happening on the left and on the right hand side with the function. And this one, we do have problem because we can see we do have some discontinuity. That means we have to investigate them, but they are still in the domain, which means the value exists. I can write value at 5 is actually also 5. We can see the dot. Okay. That's what we will do. We will take all of these numbers one by one. The first one will be 1, and then 3, and then 5, and 7, and we will check continuity, or maybe discontinuity. That means I just minimize the graph, and I have number 1. That's what I'm looking for. Always when you have a question with continuity or discontinuity, okay, you have to check the limits. Please remember, limit from the left, limit from the right, and the value. And just compare these values, these numbers. Limit from the left, limit from the right, and the value. Okay? And even not looking at the graph, even having a formula, you can still make some conclusion. Okay, that means I hope the graph is not too small. Do you think you can tell me the limit? Looking at the function, what is the limit of the pink curve at the left-hand side at 1? It is 1. Thank you. What about limit from the right-hand side? It is 1. Thank you. And what about the value? Do we have the value at 1? No, does not exist, which it's the same thing. I use the set notation, which is like empty cross dot. Okay? Because you can think about the vertical line, and the vertical line will have no intersection. Okay, that means now let me just, probably you know, but let me put nicely the conclusion. Limit exists because if the left and the right hand side is the same, the limit exists, and value is different. And graphically, we can see what is the situation. Limit exists, which means function like kind of like this almost the same thing on the left and on the right side, but we do have 1 point gone. I can, of course, we can see 1 point is gone because the value doesn't exist. Okay, that's me. What do you think? Do you possibly know the name of this type of discontinuity? Maybe it's removable. Thank you. It's removable discontinuity. Okay, excellent. Some of the textbook, especially the algebra text, not algebra, it's still calculus. Calculus textbooks, maybe from high school, they're using different words. They're using like, oh no, I don't even, like 1 point removed, or maybe point. But we will call removable because we will follow the terminology from our textbook. Okay, that means you can note what is happening. That's the situation. Okay, just one point is removed, and limit exists. As we can see, limit exists. Then we can say it's removable discontinuity. Okay, let me check because, one thing. I think somebody didn't, we have to mute the microphone, Cody, Allison, I don't know which, I will, hang on. Everybody has to mute, stop the video and mute the microphone. Okay, because otherwise it's messy and we don't want to hear. Theoretically, you should be in the nice, quiet room, right? No locked room. Nobody should enter you. But I know situation sometimes is different. That means always mute your microphone. Thank you. Okay, we do have removable. I can tell you we do have 3 different types of discontinuity. That means let's investigate the next one. Next one is happening at 3. Yeah, we can see the graph and the same thing. Limit from the left, limit from the right, value. Okay, now ready to type. What is the limit of the function at 3 from the left-hand side? Limit is, lots of answers. Yes, I think it is -1. Excellent. I'm trying to look at this small graph. Okay, limit of the function at 3 from the right-hand side. Oh, yes, good eyes, 4. Okay, you understand the limits, good. And can you tell me the value of the function at 3? Yes, because we're looking at the, thank you, Joe, thank you, Luna, I don't know if I'm pronouncing correctly, but it is -1, because we're looking at the solid dot, which corresponds to the x equals to 3. Excellent. Okay, that means now we can see, based on the limits, also not seeing the graph, later we should be able to say the type of discontinuity. As soon as you see 2 different limits, as we can see, this limit from the left is different than from the right. Okay, that means we will see that function does completely different things from the left and from the right. That means when we have this value 3, function is like doing something and stopping here, and then doing something and stopping here. That means function, let me actually put the conclusion, limit theoretically doesn't exist. Because it's true. If the limit on the left and on the right is different, then it's undefined. We do have value, but of course doesn't matter because I can't even compare. They are not the same. That means, what do you think, looking at the graph, what will be the name of this behavior, this discontinuity? It's jump. Thank you, Ryan. It is jump because function is, we can see how big jump. Yes, different from -1 to 4. Function is simply jumping. Function is simply jumping. That means yes, thank you. This is the jump discontinuity. Okay, that means you learn removable and jump. Let's keep working. We still have 2 points, 5 and 7. 5. The same thing, but x5. Limit from the left, limit from the right, and the value. Okay, now ready. What is the limit of the function at 5 from the left-hand side? Who can tell me? Yeah, I know. It is 1. What about limit at 5 from the right-hand side? It is also 1. Yes, because we can see function does the same thing on the left and on the right-hand side. What about the value at 5? Exactly the value. It is 5. Is the solid dot on the top. That's my conclusion. Limit actually exists is 1, value exists is 5, but it's different. Okay? That means, what do you think? What is this situation? It's actually one of the type that we just learned. It's still removable. Thank you, Ryan. It's still removable because I know probably, and if I'm wrong, you can tell me, but I think the common mistake is, in this case, is to think that this is jump discontinuity. Because you will be looking at this point and you will say, oh, 1 point is like jump. But no, what we're looking how function behaves. One more time. Oh, no. one more time. Do you remember? You look how at 3, how function jumped, completely different position. At 5, the curve is not jumping. It's exactly this at the same point from the left and from the right hand side, and we can see. Okay? That means jump discontinuity, it's always when the limits are different, the left and the right. If the limit is the same, of course, the value is somewhere else. At 1, we did have removable. The value was not even there. That's also the case. 1 point is taken away completely. At 5, point is also removed. And it's, I can say this way, it's placed here. Doesn't matter if it's placed here, or it's completely removed. It's still looking at the function, it's still removable. Okay, that's mean, please do not make the mistake, especially when you see the graph. But that's removable. We can see nice smooth function, just 1 point removed. Okay, and then we have x equals to 7. I don't know if my graph is nice and clear, but at 7, I really wanted to have an asymptote. Okay, I hope I didn't mess up. Okay, the same thing. Limit from the left, limit from the right, and the value. That's mean, what do you think? What is the limit at the left-hand side? At 7, it's infinity. We can see function is going up, and it's approaching huge numbers, positive infinity. And what about the limit from the right-hand side? It's also positive infinity. Thank you. Nice participation. Excellent. And what about value at 7? Thank you, Daniel. It's yes, thank you. It's undefined. Usually we don't have, sometimes for the really, really weird piece-defined function, we may have a solid point on the asymptote, but normally we don't. I mean, we could. Okay, that's the conclusion that I can write. And of course, limit doesn't matter, exist or doesn't exist. In this case, we don't have the limit, but this is the point. The type of the limit will tell me what kind of discontinuity. Do you think you can tell me what kind of discontinuity is this one? Yeah, it's just the same like the name of that symbol. Yes, somebody can type and I can show you. It's just, yes, okay, oh, nice, okay. Discontinuity. Actually, if we will say discontinuity at infinity, means that we're going to the infinity in the horizontal direction. Okay, that's mean this actually looks a little bit, this will, because you did change horizontal, and it's just the, yes, just the, but thank you for, it's nice interpretation, and I understand what, Ryan, what do you mean? But we can simply say, yes, infinite discontinuity, because it's still at 7. Yes, yes. I mean, it's fine. That's the point of participating in the classroom. Yes, we always have answers close enough, and I always, yeah. Yes, thank you everyone for typing. I'm really, really enjoying. That means it's still discontinuity at the number, but it's infinite. And how can, like, even if you're not seeing the graph, please remember, as soon as you see one of this infinity, even just one, we can always call infinite discontinuity. Because sometimes, again, for the piece-defined function, we may have just infinity on one side, and on the other side we may have a graph. I mean, we may have a point. Let's say something maybe like that. We may have function like that. That's when we can see on the left-hand side, we even have a value. The limit is 2. On the right-hand side, the limit is infinity. We will still call this infinite discontinuity. Okay? Please remember, we can't even call jump, because jump means that we're jumping from one finite point to the other finite point. We have indefinitely infinite. That means this graph will be always infinite discontinuity. But let me remove it, because we don't want to be. Okay, that means now you're confident. We do have a few more things in this section, but I hope you're confident with these 3 types. Now let's look at my, actually, okay, we do have graph, okay. Okay, now question like that. where are the following function discontinuous? That's what we have. We do have two parts, two pieces. One of them is the rational function, and it's defined everywhere, but not at 2. And the value 1 is defined only at 2. Yeah, that means this is probably like a dot value. At 2 is 1. And the graph, like the curve, will be everywhere, but not at 2. That means what we can see, this is rational function. And we know that rational functions are smooth functions if we, of course, remove the points that are not in the domain. That means this function is continuous everywhere, not at 2. And this is the straight line 1, but we only taking 1 point. That means what we have to do, we have to realize that the value 2 is giving me like a problem. That means I did identify my value that is giving me a problem, like we did previously for the graph. But for the graph was easy because you did see the graph. Now, based on this, based on the formula, I know that I have to investigate 2. And the same procedure, limit. Oh, I didn't want you to see this. Okay, no. I will write it down. Limit as x goes to 2 from the right-hand side, and then of the function, on the left. Okay? But before I start, and of course the value, okay? I will remove value. That means you can probably tell me what is the value at 2. Yeah, based on the formula, it's 1. Thank you. It's 1 because we can see at 2 is only that value 1. Okay. Oh, I see Ryan typed 0/0. Yes, good. But do you remember? Hopefully you did watch Practice with Kasia, and I did, or even my last week session. 0/0. It's not, most likely it's not 0. Okay. Do not pick 0 because 0 will be always the option on the multiple choice question on your test, quiz or midterms finals. Do not pick 0 unless you really have a strong reason to do this. Always do the work like we will do now. Okay, that means value is 1. We have to investigate the limit. But since the same formula is defined on the left and on the right-hand side, I can probably just try to compute just limit at 2. If at the end I will still need to split because I will be not able to tell, then I will do. But now I will just try to combine, just the shortcut. Okay, and the function is x minus 2. Okay, and that's the limit. That's what we can see, section 1.6. First of all, we can do direct substitution. If I substitute 2, I'm getting 0/0. That's what Ryan told us. But we know that this is indeterminate form, or we can call undefined at the moment. And we have to find 0/0 is telling me that the function on the top and function on the bottom has a common factor at 2. Let's find out. Okay, I will limit and who can help me to factor out x minus 2, x plus 2? Let's see, minus and plus, and I will double check -2 and -1. Yes, excellent. That means we can nicely see the common 0 is gone. I should maybe use the green color because corresponds to that zeros. Yeah, that you can see that was the problem, 0/0. I did cancel out that 0. And now I can substitute instead of x 2. 2 plus 1, it is 3. Okay, that means my limit is free, limit exists, on both sides it's free, and the value is different. Without graphing, do you think what kind of discontinuity we have? Limit exists on both sides, and value is somewhere else. Just value is somewhere else. What type of discontinuity? No, function is not jumping. We can see limit from both sides. It's simply 1 point is removed. Correct. And what we can do, I did simplify my function to just x plus 1. That means I can draw, I think I typed this, but okay, I will. I can draw, because this rational function I did simplify to x plus 1. I mean, x plus 1 is just the line with x-intercept -1 and y-intercept 1. However, I do not have value at 2. At 2 is simply an open dot. I can maybe write. And this is at the level 3. Okay? And the value at 2 is actually 1. The solid dot is here. Okay, that's when we can see this is the graph of the function. Just one point is removed from that line because function is not defined at 2. At 2, we have completely different value. Okay, but thank you for, yes, for realizing if the limit exists the same from the left and from the right, it's always, I mean, it's not jump, it's not jump. Yeah. Most likely it's the removable, unless this value is the same. If this will be 3, yeah, then we will have continuous function, yeah, because this dot will fill out that empty circle. Okay, and I believe I typed. Okay, let me. Shall I remove everything? Okay, I will remove it. I will remove it because we did everything you will have on the video. Okay. You will have everything on the video. I'm gonna probably make a hole in my screen because I'm trying to. Okay. And that we can see, that's the same thing. A nice graph. Okay, let's keep working. Good, yes, good participation. Okay, this question is a little bit long and we will not really, I can just show you the solution. We will probably, I will go a little bit faster. But this question is asking the other way. I'm giving you the formula and the formula is a little bit more complex than the previous one. Okay, and the same thing. We have to investigate all of the types of discontinuity. That means theoretically it's similar to this question, as you can see, but this formula was much, much shorter. But what I just want you to tell me what points, what values of x we have to investigate. Okay, that means first part, first piece, maybe I can. Hang on. Oh, no, I don't want to show you. I just wanted to draw. Yes, I can see 2, Daniel, 2 and 4 is good, but we drew. Oh, I will draw something for you. Okay, that we do have a number line. We have one formula, the second one, and the third one. The first formula is defined for all of the values less than 0. That means we definitely have 0 and 3. Can you see always that are dividing the number line? We have to investigate. That means formula on the left-hand side at 0 is the first one. Good. Between 0 and 3, we may see is this one. X, I can possibly factor out. Okay, and after 3 is the last one. I can rewrite a little bit because of course we will need this. That we can nicely see left and the right hand side, left and the right hand side. If we need a limit, 0 from the left hand side, that formula. 0 from the right hand side, this one. 3 from the left, this one. 3 from the right, this one. And we can see nicely, I just put this on the number line. Okay, that means definitely I have to investigate 0 and 3. As we can see, because always from that. But also, I think Daniel is giving us the numbers. Yes, 2 and 4, and I think that will be the case. But let's start from the beginning. The first formula is defined on that interval. We see this. And what do you think? Looking at this formula, what is the number that is still not in the domain? it's -2. That means -2 is not in the domain. This will be my another number to investigate, -2. Okay? Okay, looking at this formula, what values are not in the domain of this rational function? 0 and 2, excellent. 0 is actually, can you see we don't have the equal sign? That means 0 is already gone, but thank you, it's important to realize that. That means 0 I will not, yes, I will not write down, but 2, it's important, my next number. And the last one, what value I have to, it's 4, of course. That's when you can see, that's the reason that I said at the beginning of this question, it's a long question because now you know the process. I have to take -2, check the limit from the left, the right, and the value. But actually, -2 will not give me the value. Okay, I do have all of these numbers. I mean, value at -2 is undefined. Value at 2 is undefined. And the value at 4 is undefined. Wherever we have points that are not in the domain, okay? 0 and 3 actually are in the domain, okay? They are in the domain, that means we will have the value, but we can see we have no value. The next step, even if we don't have the value, we still have to investigate the limits because we may have jump or removable discontinuity. Okay, but again, we have to take all of these points and check the limit from the left and the right, left, right, left, right, left, right, and the corresponding values. Left, right, left, right, left, right, which actually for the -2, 2, and 4, left and the right, I will use the same formula. We can see corresponds to this one. The only 0 and 3 has different formulas. I don't want to draw the asymptote because I don't know, but we can see 0 from the left, 0 from the right, and the same. Okay, that means I do have the whole work. Let's maybe look at the first two. We will go a little bit faster, okay? But I can still ask you a questions. Okay, that means the same thing, formula and -2. Limit from the left, limit from the right, and the value. Actually, you know, we can maybe practice these limits. I mean, you can practice. Maybe I'm just overthinking. Maybe it's not difficult. I mean, not long. Okay. What do you think? Now we don't have the graph. That means, what do you think? What is the limit at -2 from the left-hand side of this function, of this formula? 2 over x plus 2. Do you think you can tell me? Because actually it's important limit. Negative infinity. Okay, we can, right, okay. Because what direct substitution is telling me? Direct substitution is telling me 2 over 0. Okay, I did make a shortcut, but 2 over 0. I did substitute -2. 2, -2 plus 2, 0. If we have a number, like a constant number over small, it's always big. Yes, 1 over small is big. But we have to check if it's positive on the positive or negative side. That means 0 is theoretically not 0, it's just a small number. Because -2 from the left-hand side is like -2.1. -2.1 plus 2 will give me negative number. Okay, I can say it's a small number negative. That means this will be a negative infinity. Really good. Okay, now using the same thing, what will be the next limit? It's also 2 over 0, but in this case it's 1.9, -1.9. It's positive. It's positive infinity. Okay, and value, we just learned that the value is undefined because of the number -2 not being in the domain. Okay. That's when we have this situation. Can you tell me the type of discontinuity? What type of discontinuity it is? Because we definitely have, it's just the infinite. Thank you. Or it's not removable because we can see the limits are infinity. Always when you see infinity, always is infinite discontinuity, even if it's just one limit like that. Okay, that means probably at -2, okay, we will have from the left-hand side, function will go down. On the right-hand side, function will go up. I still don't know the rest of the function. Okay, okay, done. 0. Limit from the left, you can see I did use this formula. Limit from the right, I used the middle one, but I did simplify. Yes, we remember the number line that I provide at the beginning. We can cancel out x's and we have 1 over x minus 2 and the value. Okay, that means, oh, that's actually easy. You can just simply do the direct substitution. What is limit at 0 from the left of this formula? Oh, you can substitute, it's 1, thank you. And what about the limit on the right-hand side? On the right-hand side is -half, really good. And what about the value? What do you think? Which formula shall I use for the value? I don't know, the graph is a little bit tiny, but can you see that equal sign? We always looking at the function that is equal, exactly corresponds to that point. Not greater than or less than, not before or after, not like on the positive or negative side. It's exactly equal to 0 is that formula. That means I think we will use this one, 2 over 2 is 1. Okay, that means limit doesn't exist, but we see the reason. We have 2 different limits on the left and on the right-hand side. What do you think? What kind of discontinuity? No, it's simply jump. Always jump discontinuity. Please remember, always jump when it's two different limits. That's what we have. At -2, graph was like that. At 0 from the left, function is approaching 1, and it's also the value. And from the right-hand side, function is, I don't know, it's approaching -half. I'm trying to get the graph. Okay, you can see. I took 1 from the left, -half from the right-hand side, and 1 as a value. Okay, let's keep working. 2. Limit from the left, limit from the right. We're actually using the same. If you copy the number line that I provided, you will see that we have to use both, because 2 is in the middle of that, between 0 and 3. That means we have to use this formula and the value. Okay, again, 1 over 0, 1 over small is big, but we have to investigate which big, negative or positive. Okay, can you tell me the first one? It's positive infinity or negative infinity? It's negative, Joe, let me check, because this is 1.9 minus 2, yes, will give me -0, negative infinity, and respectively positive. Do we have the value at 2? We remember was the middle part defined at 2, no value. Okay, again, what type of discontinuity? Oh, yes, we do have, yes, oh, no, never jump. If you see infinite, symbol of infinity, always, yes, always infinity. I know you're probably saying because it's different. It's negative and positive. Oh yeah, I can see this. But no, it's simply infinite. Always the infinity will tell me this. Okay, that means what was the graph? Shall we copy? -2 was like that. Oh no, 2. At 0 was 1 and -half, and now I am at 2. At 2, we do have another asymptote. On the left-hand side, function will go down, and on the right-hand side, function will go up. Good, and no value, of course, no value. Okay, and we have 3 and 4, 2 more. Okay, limit from the left, I will use this formula. Limit from the right-hand side, I will use this one. Yeah, you probably notice I can also simplify this way. Oh, And this one I can cancel out, but will give me negative value because it's the opposite. They switch x minus 4, 4 minus x. Okay. Okay, and the value at 3. I think this one is just direct substitution. No zeros in the denominator, no problem. Okay, who can tell me the first limit from the left-hand side? I hope we are still there. Oh, can you just substitute 3? You can just substitute 3, and I think it's 1. Thank you. 1, did I type? Yes, I did type. And what about this one? Negative 7. And now the value. Who can give me the value? Which formula we have to use for the value? Yes, thank you. The bottom one, because it's equal to 3. Really good. That means what is the value? Is the same like, oh no, should be the same because that's the bottom formula. You probably, I know what you did. You did substitute and maybe, yes, it's because it's the same formula. This formula is the same like this one. We're simplifying. Yes, thank you for calculating. Okay, that's me now. Again, test. I'm testing you. What type of discontinuity at 3? Daniel, Luna, I think Luna, jump. Okay, somebody else. Let's wait for some more confirmation. Do you agree with? Everybody agree with the jump? Oh, yes, because you can see always 2 different limits. Yes, Samuel, thank you. 2 different limits will tell me jump. Yeah, I am writing this nice like conclusion, but maybe just this is enough. Yeah, because we can see right away, different limit, function is jumping. That means we can try to, do I remember all of them? Negative 2, down and up. 1, negative half. 2, down and up. And at 3, what we have at 3? From the left-hand side, we do have 1. Oh, that's 1. And we do have negative 7, let me put here, at right-hand side. Okay? Okay, and one more, 4. Limit from the left, limit from the right, because 4 is after 3. That means we can use this formula for both of them, and the value. Okay, can you tell me the limit from the left and the right? No ratio, no. Yes, just simply substitution. And what about the value? Value at 4. Do you? Yeah, we have to be careful because do you see the formula which is not simplified? Function is not defined at 4. 4 was one of the numbers that we don't have the domain. It's so easy to say the same value, I know, but we have to remember that even if this is simply, it's different, looks different, but it's the same formula. We just simplifying for the calculation, but we still remember this came from this rational function, and this rational form is not defined at 4. Limit exists, but no value. Okay, what type of discontinuity? Who can tell me? Limit exists, but no value, no removable, just 1 point is removed. Okay, and I think I can show you this. That's the graph that I was trying to draw step by step. Okay, I think now you really understand the continuity or discontinuity. Okay, now let's solve. I still have 2 things in this section, but I think it's not too long. But what I would like to show you, the exam type question, the quiz type question. Do you have some questions so far? Okay, let's see. We know that, this is just like the kind of like a confirmation. The function f, it's continuous on the whole interval if it is continuous at every single number in that interval. Yeah, probably sometimes the mathematics definition are so like obvious. You're like stating really like a common sense, but we have to write down. And then we know the right and the left endpoints. We know that. Okay, before I show you the exam type question, I still have few things. Now what we can do, as soon as we have two continuous functions, f and g, at the point A, we can like add them, subtract them, multiply by constant, multiply by each other, divide them, of course, making sure that the value in the denominator is not 0. And we will also create a continuous function. That means adding two continuous functions, subtracting, or making all of the other arithmetic operation, we can get continuity. Also, we can try to compound a function with the other function. If both of them are continuous, then the composition is also a continuous function. Okay? Just for your information. And another property, another theorem. What we do have a few types of functions. For example, the easiest one is polynomial. Okay? That means polynomial is nice and smooth curve. Always continuous and everywhere. Okay? That's what we can say. We can say the polynomial functions are continuous on the domain. Okay? And since domain is already numbers, it's just, yeah, it's simply everywhere. But now this is tricky. Rational functions are also continuous function wherever they are defined. That means let's take maybe the easiest rational function, 1 over x. 1 over x is just the hyperbola here and here. And what do you think? Looking at the graph, would you tell me that this is continuous function? No, of course not, because what you see? You see 0, okay? And what kind of discontinuity we see? We see a vertical asymptote. It's the infinite, thank you, because the limit we can see, the functions going up and down, this will be infinite discontinuity, of course. That means everything is fine, correct. But now let's just double check this second sentence. The rational function is continuous wherever is defined. That means what's happened now, what mathematician wants? They want us to look at these two curves as a continuous curve, but we're not looking at the number that is not in the domain. That means 0 is not in the domain, as we can see clearly, it's not in the domain, and we're not even looking. Okay, we're not looking at that 0. We're just looking at that part on the negative side. That's what do you think? This curve, do you think it's continuous curve? Just this part? Yes, of course. Thank you. Because I can draw without lifting the pen, it's continuous curve. And the same situation is on the right-hand side. That means that's what this theorem is telling us, that if we're looking just at the domains, not the numbers that are not in the domain, each rational function is continuous function. Right? It's helpful property. And the same with the root function and trigonometric functions. Because we know, like, for example, tangent of x has lots of asymptotes. That means we will also say, oh, we have discontinuity. However, we have to ignore the asymptotes, ignore the numbers that are not in the domain, and just look at the curve between. Okay, that's nice question. Now, I do have a question that is testing this. Okay. That means find the largest set of points for which the following function is continuous function. That's what we have to do. We simply have to find the domain. If I will be teaching like a just pre-calculus class or even algebra, I can ask almost the same question, but I can ask, please find the domain of this function. Because we know that if I will find the domain of the rational function, this will be the intervals that function is continuous, because I'm not looking at the numbers that are not in the domain. That's what do you think? What's the domain of this function? What numbers are not in the domain? Can you tell me? 3 and -3, really good. Okay, and what other numbers I have to remove? 3 and negative 3. And what are the other numbers? Can you see the top? Yes, I have to remove negative. That means I can take only positive numbers. And on my way, I have to remove 3. I also have to remove negative 3, but negative 3, it's automatically not a positive number. Okay, that means, oh, this is a domain from 0 to infinity, not including 3 and negative 3, but negative 3 again is outside. Okay, that means from 0 to 3, from 3 to infinity. That's the domain. So you can see just the domain, but it's giving me an intervals of continuity, this one and this one. Not looking at 0, not looking at 3, because probably I will get some infinity or other discontinuity. No, just between these numbers. Okay. And then I have the exam type question. Okay. See, now let's see. You will open your quiz, weekly quiz or midterm or final, and you will see something like that. For what value of B is the following function continuous everywhere? Okay. That's what I see. I see one piece defined for x less than 1. I see this piece defined exactly at 1, which I can write right away that value at 1 is B. And I see the second piece defined after 1, for x greater than 1. All of them are polynomials. That means I'm not worried to investigate some numbers inside. No, the only number that is giving me a headache, that is giving me a problem, it's 1. Okay? Because we can see at 1, everything happens. On the left is different function. On the right is different function. Exactly at 1 is the B value. And what I want the function to be continuous, which means limit as x goes to 1 from the left-hand side must be the same like the limit at 1 from the right-hand side. And of course, the same like the value, but the value is B. Okay? That means limit from the left, limit from the right, and the value. All of them, they have to be the same. That means let's maybe, because it's too many equations, let's focus on this first. Limit from the left. Which formula I have to use for the left? Who can tell me from the left and for the right? For the left-hand side, left at 1, yes, I think it's the first one, x squared plus ax. And the right-hand side is actually the last one. Yes, 2, 2x, okay, the typing it's, I know, the typing it's not easy. 5, okay. And now I can try to use, calculate the limit. X is 1, I can just substitute 1. 1 plus a, 2 minus 2a plus 5. Okay, that means I did get an equation with the unknown a. Who can calculate the a for me? Oh, linear equation. Who can calculate? We can add 2a to both sides, subtract 1 from both sides. Oh, I'm trying to calculate. 3a. Are you calculating? It's 2, because let's see, 2, okay, 3a is 6, yes, thank you, Ryan, that's what and then a is 2, excellent. Okay, that means a is 2. And then what? What do you think? What is the next step? I still have to find the value of b. That means, what do you think? What is the value of b if a is 2? Who can tell me this? It's nice, extremely nice last step. Yeah? If the a is 2, we can see b is the value at 1, but value at 1 must be exactly the same like the right and the left-hand side limit. Do you think you can tell me now having the value, what is the left-hand side limit? And the right-hand side limit. Limit, they have to be the same. Limit, and they will be the same like the value, and this will be my b value. Okay, what is this? What is the left-hand side limit? You have the value of a. Can you just substitute? It is free. Thank you. It's simply, can you see this line? 1 plus a. 1 plus a. 1 plus a, it's free. You can try to substitute here. 2 minus 2 times 2 plus 5. I didn't even calculate, but I'm guessing must be 3. That means this is the value of b. And we can see it's just kind of like using what I got to like getting backwards and substituting. Okay, that means the value of b is 3. Okay, that means this is the nice, like an exam type question. You can double check the module practice with Kasia, and I will solve more of those problems, okay? Because we like to ask this way. Okay, I have another one, but you can I will skip this one. You can try to do it almost the same way like number 5, but you can check the solution on the additional video practice with Kasia. Oh, another one? Okay. That means these two you can practice and check against my solution. Okay, the last thing in this section is the intermediate value theorem. That means I can tell you what it is. Maybe we can solve one question and we will be done. Okay, 10 minutes. Do you think you can stay with me 10 minutes? I hope. Thank you. I was planning to have the 1 hour session, but sometimes yeah, it's longer. Okay, that's what we have. Yes, thank you. Thank you very much. Ah, you nice, yes, nice kids. I wish to have the eye contact with you. But of course, it's the online class, but at least I see your names. We can probably try to share the video, but it will be messy. Okay, maybe one day we will share the video and I will look at everyone. Okay, intermediate value theorem. What is telling me? Suppose that f is continuous function on the closed interval. That we have closed interval from a to b and nice and smooth curve. For example, that blue curve. And let n be a number between the values f of a and f of b. That means n is simply a horizontal line between f of a and f of b, where the values of a and b are different. That we can see the values of the corresponding f of a value for a and b, they are different. Then there exists a number c, okay, in that interval from a to b, such that the value at c is exactly n. Okay, that's what you can see. It's, I mean, probably you can read this a few times because we always have to read and digest every single word. But basically what this means, if I have continuous function and if I will draw, if I will pick a number, okay, if I will pick, I think I can start with this way. That's what the theorem is telling. Having a continuous function and drawing a horizontal line just between the values, like line n, right? N, this line will always intersect a curve. And this intersection, the corresponding x, will always fall between a and b. Yes, we can see for this one, we even have 3 intersections. And all of these intersections, all of the corresponding x values will be always placed between a and b. That means basically, this is the intermediate value theorem. Okay? That we will always find the corresponding x value in this. And what we have in mathematics, we do have something like we call existence theorem. And this is actually one of them. Because can you see this? This property, this theorem, it's only telling me that this number exists. Okay, this is telling me, sometimes I don't even have to compute exactly this number. No, I don't have to. I can prove that these numbers like C sub 1, C sub 2, C sub 3, they definitely exist between A and B. And for some of the models, some of the, like the mathematical coding or programming, it will be enough. Yeah, for some engineers, some mathematicians, will be enough. Okay, that means we do have a numbers between A and B. Fine, that's what I need. Okay. Occasionally, if it's the nice easy question, we may still ask you to compute this point C. But normally we will just prove that this exists. Okay. Now let's see. Of course, if we have discontinuity, it's not true. Because if I can come back here, let's say it will happen that actually exactly at this point I have discontinuity. Then my horizontal line is not even intersecting. Okay, that means of course we're talking about continuous function. Okay. That's the same thing. I'm just looking. Oh, for example, question like that. Show that there is a root of the equation between 1 and 2. Of course, root means solution of this equation. That means I want the value of x that will give me 0. Right? That means it's not easy to figure out, but what we can do, I can name the left-hand side of this equation just as a function, f of x. Okay? Actually, first of all, I should ask you, do you think it's easy to solve this equation? It's the third degree polynomial, and maybe you can try, but I can tell you sometimes it's not easy because it looks like good for grouping, but I don't think the coefficients are helpful. Okay, that we can see it's not easy. It's not easy equation to solve it. Probably the solution exists, but we will need help with some computer. But what I can do, I can only prove that there is, you can see, exists a solution of this equation, and the solution is between 1 and 2. That's what I can do. I can name this equation left-hand side as a function, and I want this function to be 0. Okay? That means my horizontal line must be the x-axis, the value 0, n equals to 0. Okay? We will do the calculation. That means I don't know how function looks like, but possibly I can draw something, maybe like that. Okay. And this is 1 of the 0, and I want this to be between 1 and 2. Okay? We do have, because they just asking us to prove that one root exists between 1 and 2. Okay? I do have another one, but I don't have to care. I have to find this one. And this is my n value. I think that was kind of like a yellow line. That means I have to prove that this n, the 0, okay, it's definitely will intersect, the corresponding x value will be between 1 and 2. That means what we have to do, in order to have the function intersect x-axis at here, would be nice to have the corresponding value for 1. This is the corresponding value for 1. Yeah, let's see this situation. And this is the corresponding value for 2. That means, can you see what's happened? One value is above the x-axis, one value is below. Because if we will have, that's actually the guarantee. If we will have the situation, one value above, one value below. Okay, like this is for 1, this is for 2. That's the corresponding values. If the function is continuous function, which this is continuous function, in order to connect them, I have to intersect x-axis. You can see that this is the point to prove that this intersect will exist between 1 and 2. That means what I have to find the value, and I have to find the value for 2. Because 1 and 2, that's the number scale from. And what I'm expecting,
I'm expecting one value to be positive, one value negative. Because we may also have the situation the other way. Below 1 and 2. One negative, one positive. I have to connect them and I will go through x-axis. That's what I want. This will be my 0. This will be my solution, root of my equation. That means let's just do the arithmetic. You have to help me because I have to take this formula and substitute 1 and 2. Do we have some? Okay, that's what's the value for 1? 4 minus 6 plus 3 minus 2. Oh, Daniel, did you answer negative 1? Or maybe that was the old answer. Negative 8. And yes, okay, that means negative 1. Actually, this one works. That means this is below the x-axis, negative. And as soon as this is positive, that's the guarantee. Okay, but who can help me? 4 times 8 minus 6 times 4, it is 12. 3 times 2 minus 2. Oh, this is 32, this is 24, and this will be 4. It's okay, I will not even finish, but this is definitely greater than 0. It is 12? I think it is 12. Good. That means this value is 12. That means, please remember, that's the point. One number negative, one number positive. Could be either way, doesn't matter. Then always we will intersect x-axis and we will meet the value 0. Okay? That means that's definitely the guarantee that the solution of this equation exists between 1 and 2. Okay? So now let's just, shall we finish or shall we solve? This is the solution. Okay, maybe this question, okay, let's solve this one. This will be the last one because you may see this question. Okay, that means this is the same what we just did. According to the intermediate value theorem, which of the polynomials below must have a real root? Real root means the solution of this equation, okay, like the value 0. Which means which of these polynomials will intersect the x-axis between -1 and 0. Okay, that means what we have to do is a little bit time consuming, but we have to take each polynomial one by one and test the value for -1 and for 0. If one of them is positive, one of them is negative, it will tell me, okay, let's say the value for -1 is negative, the value for 0, it's positive. This is telling me that I will intersect the x-axis, real root, real solution, real x-intercept. That means let's try. You will help me do the arithmetic and we will be finished. That's everything for today. Let's take the first one. Value for -1 and value for 0. For 0 is easy. I can do it, -4. Okay, who can substitute -1? -1, -3, positive, -3, -4. Okay, that's what I see. This is negative and this is negative. Not good. If I have two negatives, that's not a guarantee. Okay, let's test B. Value at -1, value at 0. At 0 is -1. Okay, who can tell me value at -1? -1. It's -2, -3. Oh, I think it's even more than negative. Am I right? Yeah, I think it's actually doesn't matter. All of them are, yes, all of them are negative. That means that's not a guarantee. I am looking for one negative, one positive. Okay, let's check C. F of -1, f of 0. 0 is nice and easy. Okay, -1, +2, -4 -1. I think it's still negative. Oh no. Okay, let's check D. F of -1, f of 0. Oh, f of 0 is +2. I don't have to write plus. Okay, Okay, let's say hopefully -1 will give me negative number. -1, +2, -4, +2.
Do you think it's negative number?
It is. That means this is negative, this is positive. That's what I'm looking for. If I will be on the test, I will still test this one. Okay, because just in case I make the arithmetic mistake. That means this is 5, and this will give me negative, positive, negative, positive. Okay, that means both of them are positive. Also not good. Please remember. Okay, that means that's what we want. We want one value positive, one value negative. Either way, this means that connecting them, I will go through the x-intercept, real root of the equation. Okay, thank you very much for today's session. Thank you.